Yeah, the last bit of this section of trapezium rule is to do with how to determine an error in the calculated approximated value using trapezium rule. So in applied math, we say an error is a degree of inexactness or the difference between the exact and the approximate value. And since it is the difference between the exact and the approximate value, we say that an error is a deviation from the exact value. So an error is given by the exact value minus the approximate value. If they do not request you to determine an error, then they will tell you to calculate the absolute error. But the absolute error is the magnitude of the error. So you go to the error and you put their magnitude signs, implying that if the difference is a negative, then you conclude with a positive. And if it is a positive, then you maintain your final answer. Relative error is the absolute error over the exact value. We shall see when we reach error propagation that we shall redefine our relative error to be absolute error over the approximated value. But now if you are in trapezium rule, we say that relative error is absolute error over the exact value, where the exact value, that is the value that is obtained using the methods of integration, which are basically taught in pure math. Then the approximate value is a value that is obtained using trapezium rule, which we have just studied in applied math. So our relative error this side in trapezium rule, it is absolute error over the exact value. If it is not that, then they will tell you to calculate the percentage error, and the percentage error is relative error times 100%. And since relative error is absolute over exact, then it is absolute over exact times 100%. So generally, in integration, we are picking the simplest integral and we check how we can determine the exact value. So this generally is to do with how do we calculate the exact value given a simple integral. For instance, an integral from a to b of x power n dx. We increase the power by 1 and we divide by the new power, but we have integrated from a up to b. So if you increase the power by 1, then the new power becomes n plus 1. Then you divide by this new power, which is n plus 1. So this is the integral of this definite integral from a to b of x power n. So here there is x, we first substitute in the upper limit, which is a b, and after subtracting, we put in the lower limit, which is an a. So this would be the exact value. So this generally, for integration, this is to do with the determination of the exact value. Because we have said all exact values are determined using methods of integration taught in paper 1, and approximate values are determined using trapezium rule. So if that is to happen, then they will give it in this sense. The question may read, use trapezium rule to estimate the area of y is equal to x squared between the x-axis, x is equal to 0 and x is equal to 1, using 6 ordinates, and you give your answer to some number of decimal places. So we said if they tell us to give the answer correct to 4 decimal places, then all these values that we enter here must be beyond 4 decimal places. All the y values must be beyond 4 decimal places for purposes of emphasis. So our part A is to use trapezium rule to estimate the value. That implies that we need the integral of this guy, which is x squared, from 0 up to 1. So if you want to use trapezium rule to get the integral the value of the integral from 0 to 1 of x squared dx, we said you relate it to the general form of an integral when this function is not defined, so that you can read off a, b, and y. So if we compare this and this, our a is 0, our b is 1, and y is x squared. So our h becomes b minus a over n, where n represents number of subintervals. And since they gave us ordinates, we are taking away 1 to get subintervals, which are equivalent to a 5. So our h will definitely become a 0.2. Then you follow the procedures and you get to this table. We said while drawing the table, you first write the first x value, the lower limit of the integral, which is a 0. After writing the lower limit of the integral, you keep on adding h, which is 0.2 on the lower limit, until when you get the upper limit. So our h is a 0.2, our starting value is a 0, plus 0.2, we get 0.2, plus 0.2, we get 0.4, plus 0.2, 0.6, 0.8, and a 1. So since we have reached the upper limit of our integral, we stop and determine the y values. We said we separate these y values because in the formula y0 and yn are added separately. Then also these ones are added separately and multiplied by a 2. So that is the essence of this line. Our y value of the first x value is this, and our y value of the last x value is this. So you add them and get this. However, we have noted and said, so when x is 0, we substitute in y is equal to x squared. Where there is x, you put a 0 to get the y value. But when recording the y values, we have said you record them if the final answer wants the value of the integral to 4 decimal places. All these ones must be written to at least 5 decimal places. That is why you're seeing my y values having 5 decimal places, because the final answer is needed to 4 decimal places. So every after substituting, we shall write our value of y to 5 decimal places, and then we enter them here. So when you add this plus this, you get this, and when you add these ones, you will definitely get that. So you will take time and confirm those values. Our target is to get the approximate value. So after adding y0 and yn, we get 1.1. So here there is y0 plus yn, we shall put this, and it is this one here. Then plus a 2, the sum of all the middle y values, which is a 1.2. It is what we have here. So we shall have a 2 into 1.2, which will give us some value there. So finally, the integral from 0 of x squared dx will approximately be equal to, where there is h, you put a 0.2, and then you substitute accordingly. So our integral from 0 to 1 of x squared dx is going to be approximately equal to, then we recorded this at 4 decimal places, because the final answer was required to a minimum of 4 decimal places. So you enter this to 5 to 5, and then you recorded this to 4 decimal places. We have done that because in some questions you may meet these y values when they are different. It is just fortunate that for us, when we enter, we can get 0.04 as our final answer. But then we are adding these zeros to ensure that if we meet any other question that requires the value of the integral to 4 decimal places, and these values after the decimal place are different, then you round them off to a minimum of 5 decimal places if the final answer is required to 4 decimal places, or if the question is open. If the question does not tell you the number of decimal places the final answer must be written to, then the final answer should be written to a minimum of 4 decimal places. So it was the essence of maintaining here the 5 decimal places, so that we can always recall that these must be recorded to 5 decimal places if the question wants the final answer to 4 decimal places. If it wants them to 5, if it wants the final answer to 5, then you record these ones to at least 6. So you have to ensure that you always record beyond the number of decimal places the final answer is required to be written to. So that is that about part A. Then part B is to do with determination of the exact value, and we said to determine the exact value we use the methods of integration from paper 1. So we shall integrate this from 0 to 1, and because it is a simple integral, we increase the power by 1 and we divide by the new power. So if we do that, our exact value will now have an equal sign. If it is an approximate value using trapezium rule, you put approximately equal to. Now that we are dealing with an exact value, it must be equal to. So our integral of x squared from 0 to 1, we are going to increase the power by 1 to make it x cubed, and we divide by the new power to make it a 3. So when you substitute in the upper limit, you get this. When you substitute in the lower limit, you get this. Where there is x, that is where we put these limits and we maintain all the other constants. So here there is x, you put your 1, becomes 1 cubed over 3 minus. These lines imply that, this first line, it implies that you are done with substituting in the upper limit. Now minus, you're now going to put in the lower limit in this expression. So here there is x, you remove it and you put a 0, it becomes 0 cubed over 3 to make it 1 over 3. Then you record your final answer to a minimum of 4 decimal places if the question has not specified. For instance, this one is just requiring us to find the exact value of this, and since it wants the exact value of that, then we are meant to, since it wants, I beg your pardon, since it wants the exact value of this guy, then we have to write our final answer to minimum of 4 decimal places because they were not specified here. Now in part C, they want the percentage error. So our percentage error is relative error over the exact value, but we said relative error is absolute error over exact, but absolute is exact minus approximation. So over the exact for the relative error times 100. So for the absolute error, we add the magnitude symbols. Where there is exact, we are going to substitute there the value of our exact value, which we have obtained using the integral, which is 0.3333. It is this guy. Where there is approximation, remove it and you put the value obtained using trapezium rule, which is a 0.3400. Where there is exact, you remove it and put the exact value, which is 0.333, and your final answer will definitely be a 2.01 to 0%. You are free to put this, or you can even not write this, the percentage symbol, the percent symbol, and you just write 2.0120, because this one is already saying that whatever you are calculating is a percentage. So since this is a percentage error, you may not write this and just write 2.0120. It will still be okay, but even if you write it, you will not be penalized. So it becomes a 2.0120. Then part D wants us to state how the error may be reduced. If they do not set it this way, they will tell you to state how you may improve on the accuracy. So we improve on the accuracy by increasing the number of ordinates If you don't want to use number of ordinance, then you say by increasing the number of strips. If not that, then you say by increasing the number of sub-intervals. So sub-intervals and strips, they are the same. Then ordinance are slightly different from the sub-intervals or strips. So you have to pick only one amongst these ones to get that one. But you can't get how to reduce or how to improve the accuracy or how to minimize the error unless when you have calculated these ones when they are very correct, because you can't minimize what you do not know. So in most cases, this mark is attached to having either the correct absolute error or the correct percentage error, depending on what the question has dictated or it wants you to calculate before getting to this question of how you can minimize the error. So you minimize the error by increasing the number of sub-intervals. If you don't use that, then you say by increasing the number of strips. If not that, then you say by increasing the number of ordinance. But you have to pick only one of these three. Then we have said that you ensure that all these calculations before are very correct before going to how you can minimize the error, because once you get a wrong answer, then you are bound to not receiving that mark on the last part. Then in your free time, you will take time and go through these. The first one is to do with what we have just covered, and it is to use trapezium rule to calculate that. Then the second one is also what we calculated earlier, only that this time we are seeing our integrals not starting. The integrals can be brought when they are not starting from a 0. So when going to the table, this one is going to be our starting value, a 1, and our last value would be a 2. So you do not promise that always the x values must start from a 0. These keep on adjusting. So we are seeing that in part A, while using trapezium rule, we are going to start with x is equal to 1 as our starting value, and we shall end with x is equal to 2. Similarly, in question 2, we are not seeing a 0, but instead a 1.3. So in this column where we have the x values, we put here the lower limit of the integral. If it is a 1, you put there a 1. If it is 1.3, you put here 1.3. Then you use h, you keep on adding it on this first value and all the subsequent values until when you get the upper limit of the integral. So that is what we shall use to check these ones, and also this and that. Then this is what we discussed earlier. Then in question 4, they are telling us to use a width of pi over 12. Then the integral is starting from pi over 6 up to pi over 2. So even in this case, where they do not give you the sub-intervals or strips or even ordinance, and they have instead given you the width, we said in the previous session that if that happens, we do not recalculate the n or even the ordinance, because we will not be having them. So what we do is to use the width as our h. So our h becomes pi over 12. Our starting x value would be pi over 6. So you begin with pi over 6, you keep on adding pi over 12 until when you get pi over 2. And if you do that, you'd be done with the x values. Then you substitute them here and you get the corresponding values of y. But you do not forget that if the function contains any trig function, any trig expression, if this contains any trig expression, then the calculator must go to radians. So finally, these are questions in the UNEB past papers. So you go to the UNEB Applied Math P4 to 5 stroke to all the curriculum. and you try out all these reference questions. You also check between 2023 and 2025 for more other questions to do with the this. So away from the trapezium rule, we are now going to switch to what we call errors, now in detail, which will introduce us to error propagation. Thank you for listening.